Good morning, everyone. How are you all doing? Good? Okay. All right. Okay. So we will do, or I will have that review session. I wasn't able to find a classroom large enough for Friday, so it'll be 100% via Zoom. And it'll be from 4 until we're done. I anticipate it'll probably be 2 to 3 hours, just going over every single question. So historically, what I prefer to do would be to have you actually go through and do an extra credit activity where you would go through every single question and you would write why your wrong answer is wrong and why the right answer is right. And so then the point of that would be for you to now demonstrate to me that you've now learned the material, because I want you to learn it. Like you got to know it before the final exam. So due to scheduling constraints and my ability to lack of ability to be able to grade all of those in a promptly manner, instead of doing that, I'm gonna have to think of some other extra credit assignment, or I'm considering just curving the exam. So that's kind of where I'm at, is trying to think of something to try to boost the scores, but I still want to emphasize that it's very, very important that you learn the material. So that's why I'm holding the review session, where I'm going to go through every single question and I will talk about why the right answers are right. And then I want you to still make sure you analyze why your answer is wrong, right? So you need to make sure that you know that so you don't make the mistake again. So I'm going to try to address any sort of common mistakes, but it'll also be good if during that, while I'm going over it, if you're like, why couldn't it have been SN1? Then that would be a really good time for me to then talk about why that answer is wrong, right? So if you're able to attend, then that would be great. So I can also address why the wrong answer is wrong. But even if you're not able to attend, at least get why the right answer is right, and then make sure that you still ask that question, right? I want you to fully understand the material so that you can be successful going forward. Okay. Are there any questions in the meantime? Okay. So just to clarify, I know that the exam was hard. It's always hard. It's organic chemistry. So I don't want you to that's why I'm looking to just boost the grades to try to correct the fact that maybe it was a little too hard, since everyone mostly did on the very low side, the surprisingly low side. So that's why I want to try to boost the grades up, because that sounds like if that many people did it poorly, that sounds like a me thing, not necessarily a you thing, but you still have to know the material. So it's still, looking over it, I still think it's a very fair exam. It just may have been too hard. So I don't know if that makes sense in that way, but it's all reasonable amount of content that I expect you to know. And it's something that you'll be expected to know when you go into Orgo 2. So you got to make sure that you know it, so that when you continue on, you can be successful in your other classes. Okay. So that's the point of trying to boost the grades, so that I don't want one exam to hurt anybody. But do take it as a lesson to make sure that you are reflecting on, do you actually understand the class material, so that you can make sure you're performing well in the future. All right. Are there any questions in general about anything? Yes. Yeah, it already was posted. So if you go to our Canvas page, go into modules, and then the graded assignments, the click here for midterms and finals. That's where you find your study guide. A blank copy of the exam was uploaded. I don't know why I clicked on it, but so there's the blank copy. The answer key and grading rubric is here. And then the exam statistics are here, which was, that's the part that really concerned me. I've had low averages before, but that one was, the distribution is what shocked me. So, but yes, all of that is available in that exam modules. So like I said, like on the summer, that was low, but in the summer, one, they'd never seen this exam format before. And I was able to do an extra credit assignment because it was the only class I was teaching. And nope, that was it. I had the time. So I was able to do that extra credit assignment. But now I'm teaching 3 classes, so I just can't, I don't have the bandwidth to be able to grade twice as many students while also having actually close to like 1,000 students this semester. So with my other classes. So yeah, I'll find another way to boost the scores up. Right. Any other questions? Yeah. So yeah, all of the graded, the regrades, sorry. So your graded exams will, yes, be returned before the review session because they're in recitation. The regrades, I'm getting them today. So I can try to make sure that all of the regrades that I receive today, I will try to make sure that they're done by Friday. So that would be like the earliest kind of turnaround. Normally it takes about a week for it. But yes, I can try. So if you are a Thursday recitation, you might want to take pictures of your exam in case you aren't able to get your exam back in time. That way you can still look at it during the review session. Yeah, that's a really good point. Right. Any other questions? Yes. Okay, yeah, so that's absolutely not a dumb question. First of all, just to my philosophy, there are no such thing as dumb questions, because if you're thinking, like if you have a question in your mind, then that means you're thinking about the class, you're thinking about the content or your grades, so it's a good question to ask, because we want to make sure we have clear communication. Okay, so to clarify how your final grades are assigned is that we don't do a curve, but it might feel like a curve. So it's technically not a curve, because what a curve is what I'm considering for this, which is just I give everyone a set percent just to try to fix the average. So that is, a curve is like, I'm gonna take this bend, I can't point to it. I'm gonna try to take this and just shift it over. So like that's a curve where I just give everyone like the same amount of percents, and I just try to like push everyone forward. So the reason I'm trying to do that is to try to help you be able to predict your final grade in the end. Because what we do is grade cuts. So the grade cut process is, instead of adjusting your score, we adjust the definition of an A, B, C, and D. So instead of it being like a 93 and above is an A, and then a 90 to 93 is an A minus, and then the 88 to 90 is a B plus, or whatever it would be. Instead, we're like, okay, well maybe a 92 to 100 is an A. And then maybe the 88 to 92 is now your A minus. So like we shift what the definition of the letter is. So like it can feel like a curve in that, yes, we are going to try to still make it a little more generous to adjust the score from the University Standard Grading Scale, but it's not a straight curve, which means that not everyone, like the gaps are different, like the adjustments aren't equal for everybody. Because what we try to do is we do try to kind of scoop a little lower so that whenever we find a gap between grades, we like boost people up a little bit more. So it might be, so instead of it being like every letter grade is like exactly 4% different, instead it might be this one's 6 because there's like a massive gap here between students. So we're like, all right, since you were close to those, we're gonna boost you up, and then it might be the next one's only like a 2% then. So like it's a weird system, but that's kind of how the grade cuts work. So because of the fact that I don't control that, I don't have any say of where that ends up. I can't tell you what your grade is, and then you can't predict it. So then that means that you could be sitting at like a 60% going, is that good or bad? I don't know. And so I don't like that. So that's why I'm trying to adjust this, because I try to keep us as close to the University Standard Grading Scale as possible so that you can predict what your grade will be in the class. So that's why I'm trying to adjust this instead of just leaving it to the grade cuts at the end. So that way you have a little bit more knowledge of like where you're progressing. So that's why I'm trying to adjust this average. So that way you can have, I mean, normally there is some like slight adjustments still, but normally I don't see, for my classes, I don't usually see more than like 1 letter grade adjustment. So like if you get a B, you're not, or if you're looking at like a university standard grading scale B, I have only once, and that was a really weird case, seen grades get moved more than just like a B to a B plus. Like normally it's just like a little nudge or nothing is where I try to keep it at. So that way you know what your grades are gonna be. I'm trying to help it be predicted or predictive. So that's why I'm trying to adjust the grades now, so that way you kind of know going into the final exam how you're performing. So yes, there will be a score adjustment at the end still. We will still have the grade cuts. It's technically not a curve because it's not equal for everybody. It's just, it's going to try to like group you based on similar performances and then be like, all right, so if you all have very similar grades, you all now become the B category. You all have similar grades, you all now become the B minus. So we try to like group that way. So it's like a clustering system. Does that make more sense? Okay, cool. Does anyone else have any questions? Okay, cool. There we go. All right. So then let's get back into our content. So we left off looking at our onium ion mechanisms, those anti-selective mechanisms. And we had said that we had those 3 are halogenation, halohydrin, and oxymercuration, demercuration. So for each of these, the whole big thing about it is that you're gonna end up with the anti-product, meaning that you have that stereochemistry where one atom, there it goes, where one atom is on the top and the other atom is on the bottom, right? So that's the anti, is one's on top, one's on bottom. For the halogenation, we ended up with 2 halogens. For our halohydrin, that's where we were adding a halogen and water. So we were hydrating and halogenating. Oxymercuration, demercuration, we said that that is where we are adding an oxygen and mercury in our first step, and then we're gonna remove the mercury in the second step. So that's where we left off, was looking at the mechanism of how do I end up with just a net alcohol in my product? Because I'm gonna add alcohol and mercury, but then remove the mercury. So all I see is the alcohol in the end. So the mechanism, remember that the key difference between this and the carbocation mechanism is that the atom, the electrophilic atom, also has a lone pair of electrons, right? So it can be both the electrophile and kind of a nucleophile. So it does this like give and take. So it's going to be attacked and then also loop back around and attack the more substituted side of our alkene. That gave us our 3-membered ring that, in this case, merconium ion intermediate, because now I have mercury in a 3-membered ring with a positive charge. And then we had water come in and attack that carbon, popping open the ring. So we attack the more substituted side, pop open the ring, just deprotonate, get it neutral. So this was the product of step 1. This is our oxymercuration part, where you get oxygen and mercury on opposite sides. And so then remember that I said you would also then get the other stereoisomer where you would see the alcohol is still on the more substituted side, right? It's still regioselective, selective. The region where the alcohol ended up, the carbon that it ended up on, is still specific. So it is still going to the more substituted side. It's just the alcohol could be on the top or the bottom, right? But no matter what, the alcohol is always on the opposite side of that mercury. That's the anti-selective part, okay? So that's our oxymercuration, makes those 2 products. The demercuration, step 2, The mechanism is not known. So, like literally, although to be fair, the last time I checked was last spring, but as of last spring, the mechanism is still not known. And I'm gonna guess it probably isn't because most organic research isn't well, it's starting to swing back to be more like chemistry for the sake of chemistry, where we're trying to do more mechanism elucidation. But largely, people care more about making the molecules, specifically usually drugs is kind of where our current push is. We have a large biology focus. So a lot of the research just isn't really focused on these old mechanisms because we know reliably this is what it does. So we don't really care about the why at the moment. Or rather, we aren't dedicating the resources to figuring out why. But that being said, we can still talk about it. So even though the mechanism isn't known exactly, we can talk about it and we can talk about how to draw reasonable curved arrows, which is why I still teach this and we talk about it because we can propose reasonable things. We might not know exactly what the perfect picture is. We might not know 100% that's what's happening, but we can have a good educated guess. By knowing our nucleophilicity and electrophilicity, we can try to predict what might be occurring. So when I think about it, in step 2, we are adding sodium borohydride. So sodium borohydride, is that going to be a nucleophile or electrophile? Nucleophile. Why? You're right. Why? What do nucleophiles have? Electrons, right? Yeah, so it's electron rich. So we saw the negative charge. So negative charge, electron rich, nucleophile. So then that means that this is going to be my electrophile. My sodium borohydride, we always used it to attack carbons, right? It was with that carbonyl addition, that's how we made our alcohols. So we added sodium borohydride to like a ketone or an aldehyde, and that gave us our alcohol, right? So we saw it with like the ketone, with sodium borohydride. That led to our alcohol. So it added in the hydrogen. The hydrogen ended up on carbon, right? So we can imagine something similar of, okay, if I know that this acts as a nucleophile, I also know that I need to get another hydrogen on this carbon, right? This is the product that I see. I have checked this. I know that this is where we end up. So I'm going to guess, all right, well, even though I don't have a carbonyl as my starting material, maybe it still does act as a nucleophile, attack that carbon, and kick out the mercury as a leaving group. So the other thing that we see in our products is I see liquid mercury. Like it's actually kind of cool. Like mercury like beads out, so you get the little droplets of liquid mercury at the bottom. So depending on how high of a concentration you have. So you would need actually a pretty large concentration to actually visualize it. But so we know that it is going to have that mercury fall out in this reaction. So that tells me that I must also have to kick out that OAC at the same time, right? So to rationalize the products that I'm observing, these are the arrows that I'm going to use to try to explain the bonds that I see, right? I know that I need to make a bond between the hydrogen and the carbon. So I draw this arrow to make a bond between the hydrogen and the carbon. I know that I need mercury to gain the arrows, and I know carbon can't have more than 4 bonds, so, or to gain the electrons. And I know mercury, sorry. I know, okay, starting again. I know that I need this carbon-hydrogen bond. That's what this arrow does. That makes the carbon-hydrogen bond. I know that I need mercury to gain the electrons. It has to ultimately be reduced. I have to go from a mercury 2 to a mercury 0. So I know that I need to go and give electrons to mercury. I also know that carbon cannot have more than 4 bonds. So I know I have to kick out something as a leaving group this is going to be my most polar bond here, and you break polar bonds. So I'm going to kick out the mercury. The fact that I see mercury as a liquid tells me that I know mercury must be left alone. So then that's why I draw this extra arrow to then kick out the OAC, the acetate, to rationalize these be my products formed. Does that make sense how we could show those arrows? Okay, so these are reasonable sets of arrows to propose what the mechanism could be. So the reason that I know this is wrong is for two reasons. One, you also need to have sodium. Oh my gosh, what am I doing? You need sodium hydroxide. You need NaOH. We didn't use that in the mechanism though, right? Like I didn't draw any arrows using it. So my arrows must not be right if I need a reagent for this to happen, but I don't use it. So sodium hydroxide's doing something that we don't know yet. It's just there. Yeah, what's up?
For the final, are we going to need to know like a proposed mechanism for this or just know what happens?
So for this, I would expect you to know like reasonable sets of arrows. So as long as you are drawing, and that's what I expect on every mechanism question, which is kind of why I'm going through this, is that no matter what question you're faced, if you're drawing like reasonable arrows, that's how we're going to get the good credit. Like that's how we get our partial credit or full credit, is to make sure that you're thinking through that inherent reactivity. So for this mechanism specifically, yeah, I would just expect you to draw like something like this would give you reasonable arrows. So then that would be absolutely a reasonable thing that would get you full credit on the final. Also to give my hand, I also wouldn't ask this because it's not known and it's hard to grade. So if you're trying to think about it from like trying to get into my head, I need to write questions that are pretty easy to grade so that we can get through all of the exams in a very short period of time so we can get finals out or the final grades submitted so it can get sent to the registrar and people can graduate potentially. So for that reason, this is not a question that I would ask, but you do need to be able to write reasonable arrows. So like if I'd asked you what would be a way that I would actually honestly frame this on an exam is I would write like these arrows and then say, like discuss why this isn't, you know, how I can know that this isn't correct. And you can say, well, I didn't use one of the reagents here. And so like the reagent isn't being used. So like it'd be an open-ended option where you'd be trying to discuss the mechanism. Or it would be like, why are these reasonable arrows? And it would be, well, they rationalize the products that are being observed. So then that would be like, that would kind of be an easier way for me to grade this content. To say, do you understand what's going on with the curved arrows? Because yes, these curved arrows explain the product, but I know that it can't be correct because I'm not using every reagent that is necessary for the reaction to occur. So yeah, this wouldn't show up in the mechanism portion, but it might show up in the open-ended portion. But if you know how to draw reasonable arrows, then you can draw any of the mechanisms in the mechanism portion. So the other reasons that I know that this is not accurate is because this product is also formed with this one. I see that the hydrogen is actually on both the top and the bottom. So if they do this with deuterium, then they can see that deuterium ended up on the top and the bottom. So then that's going to indicate that that stereochemistry is being lost. So it's telling us that it's not SN2. Because it's actually not specific in where the hydrogen ends up. So the current theory is that it's actually probably some sort of radical mechanism. And so that's usually where people go if they're like, my curved arrows don't make sense. Radicals, because radicals aren't fully understood at the moment. They're kind of like one of the new groundbreaking focuses. Not groundbreaking, but one of the current research focuses. All right, so key point of this is that this is wrong, but reasonable. And reasonable is what I want you to aim for. Like, that's what I want you to think about, is that if you can identify nucleophile, electrophile, acid, base, oxidant, reductant, that is going to be a reasonable set of arrows. And so then that is what gets you credit. So that's where I want you to aim for. I want you to be reasonable, rationalizing, I need to make the product that I see, so what are arrows that I can use that'll put electrons where I need them? So that is what's going on with the sodium borohydride reduction. Okay, so the advantage of why would I even do sodium borohydride, or sorry, why would I do the oxymercuration, demercuration? Advantage is there is no rearrangement. So when I look at my oxymercuration, demercuration, which we need that NaOH in there, oops, then what we're going to see is the alcohol ends up on the more substituted side. It is the Markovnikov product but there's no rearrangement, right? It stays on the carbon that had the double bond. So that's the benefit. If you're going through the onium ion intermediate, you never get a cation. If you don't make a cation, you don't have rearrangements. If you used just the normal hydration, you're doing strong acid with your carbocation mechanism, that means that you make that carbocation and then you have a hydride shift, because if you make a carbocation, you must make the most stable carbocation before the nucleophile can attack. So then that's going to say that you're going to still get a Markovnikov product, but with rearrangement, right? So that's the difference. So if you wanted rearrangement, great, do a carbocation. Then you would pick these reagents if you want to get the alcohol ultimately on the most substituted side. Like if you want to be at the most substituted site ever, use acid, use strong acid. If you want it to stay on the carbons that have the double bond, do oxymercuration, demercuration. Right, so that's the benefit of doing this. So these are two ways of making alcohols from our alkenes. We're going to have one more? Yeah, we'll have one more. Okay, but to summarize, so these three reactions, they generate these onium ion intermediates. So you get your three-membered ring with a positive charge. That blocks one face. That's why it is anti-specific. So then the ring opening is going to be anti-selective. We're going to consider it to be SN2 when we look at all of the other ones. And so then we will just make it simple and just say, yeah, that the ring opening is going to be, and actually not SN2. It's that SN1 type. Sorry. Because the nucleophile is attacking the more substituted side. That's why it's not SN2, right? So it's acting like that epoxide when we're opening the epoxide with strong acid. So it's that SN1 type, but it's not truly SN2 because we attack the more substituted side. SN2 attacks the less substituted side. All right, so those are our three reactions for the anti-selective reactions. All right. Are there any questions about the anti-selective reactions? Yes. So why did I need sodium hydroxide here? Yeah, we don't know. I don't know. Like I literally, I have no clue. Nobody knows. That's a great question, and I also want to know. So if you want to go into chemical research and find out, and then let me know, that'd be dope. Because yeah, it doesn't make sense. So with that, I will say, if you forget it, I won't mark it wrong. Because it is weird. So like if you forget, because clearly I forgot, like I'm not gonna mark you wrong if you forget it, because in the mechanism, it doesn't make any sense, all right? Okay. Any other questions? All right, let's move on to part 3, our sin additions. We're gonna have a lot more of them. We have 5 sin additions that we're gonna talk about. So we had 2 carbocation, 3 anti, 5 sin. For our sin selectives, we're going to have our products end up where your 2 new atoms, 2 new groups, are on the same side. And so that's what we're gonna see here, is that my hydrogens, the new elements, they're on the same side. So that's the sin addition, is same side. These will all be concerted mechanisms, and that's what's gonna make them sin. So concerted meaning one step. So what we're gonna see is we have hydrogenation. Hydrogenation is going to be adding hydrogen. So the process of adding hydrogen, we're gonna add 2 hydrogens across the bond. This palladium, this is read as palladium on carbon. The PD/C is palladium on carbon. That is a metal catalyst. The carbon is just a substrate. Substrate meaning it makes it easier to scoop out. Like it's just so that you can weigh it better. It just makes it easier. It doesn't actually do anything other than that's easier. But the palladium is going to be the metal catalyst. So remember, a catalyst is going to lower your energy of activation barrier, but not be consumed in the reaction. So it'll come out at the end unchanged. So it's not adding any elements. We don't see palladium in my product, but this is necessary. You must have palladium written here or there is no reaction. The palladium is what is actually making the reaction possible, is it's going to lower the energy of activation barrier so the reaction can occur. So you must have palladium there. It is your metal catalyst making the reaction real. Without palladium, it does not work. Our hydroboration oxidation is another 2-step reaction. So we're gonna be adding hydrogen and boron in the first step, and then we're gonna do an oxidation, which is going to add oxygen, which is gonna turn boron into oxygen, is what we're gonna do. So in the end, it's another type of hydration reaction. Or instead of saying another, I'll say our third. It's another type of hydration, because remember, hydration just means we are adding water to the molecule, which is what we see. We end up with H, 2 H's and 1 O. So the net result, so hydration is describing what the product looks like. It's not indicating the mechanism, it's just saying what does the product look like. You have hydrogen and an OH added into your structure. So that's our third type of hydration, our third way of making alcohols. This one is going to be anti-Markovnikov. That is its regiochemistry. The stereochemistry is still syn, right? Or I guess I did that backwards. Right, so it's just like how Hoffman and Zaitsev was our regiochemistry, but E and Z was our stereochemistry. Well, it's same deal. Anti-Markovnikov is the regiochemistry. That says where did the alcohol end up? The syn is the stereochemistry, which is saying that your hydrogen and your alcohol are on the same side. So the hydrogen is going to come from the BH3. And notice that this is BH3, not sodium borohydride. This isn't BH4. This is neutral hydroborane, BH3. That's going to be adding the hydrogen. Our OH is coming from our peroxide. That's what's adding the actual alcohol in the second step. So the alcohol is ending up on the less substituted side. We're getting our oxygen on that less substituted side. So the first step is going to be the syn addition. And then the second step is an oxidation. The next one we're going to talk about is going to be the dihydroxylation. So I'm just outlining a summary of all the reactions first, then we'll do our mechanisms. But the dihydroxylation is where we're going to end up with our alcohols. So di meaning two. Sorry, go back up. Hydroxylation, hydroxyl meaning OH. So the process of adding two OHs. We're going to do this with osmium tetroxide. That's the key reagent. Hydrogen peroxide is just going to be what's necessary to make it catalytic. So if you have one equivalent of your osmium tetroxide, then you actually don't need the peroxide. So osmium tetroxide is the key reagent there, adding those oxygens. And again, we are syn additions. We're getting the OH on both sides. Since it's the same element or same group adding to both sides, we can't use Markovnikov or anti-Markovnikov labels because there is no regiochemistry. Both sides get the same thing, right? So there's no difference between the left side and the right side of the double bond because they both get the same elements. So we can't use Markovnikov and anti-Markovnikov because it's the same. So dihydroxylation is going to add the two alcohols. And actually one other thing that I'm going to note here. We will also be able to do it with potassium permanganate if it is dilute and cold. The key thing here being it must be dilute and cold. Like that's really important. So if you see KMNO4 written as dilute and cold, then it will be able to stop at the diol. Potassium permanganate, remember it's the really strong oxidant. We're gonna see that it actually wants to continue to react further. It wants to make carboxylic acids. So the only way to get it to stop and not make that carboxylic acid is you gotta make it really dilute and you gotta make it really cold. And even then, it's still really hard. So normally people are gonna use the osmium tetroxide, but it technically is possible, has been done with potassium permanganate, but only if it is dilute and cold. So if you just see normal KMNO4, you're making carboxylic acids. If you see dilute and cold, both have to be written, then you can stop at the diol, because then you're stopping it, you're slowing it down. So this will be another set of reagents that will do this dihydroxylation. Our carbenes are going to be this weird thing. So carbenes, I had mentioned this, lecture 2, I think, where I said that these are these weird exceptions to our octet rule. So this should look really weird to you. This is carbon with 2 bonds, 1 lone pair, 0 charge. It is neutral. That's weird. That's a weird, unhappy carbon. It does exist, though. So this is going to be our carbene, but we're not going to be able to just add it. You can't bottle this. This does not come in a bottle. You have to add reagents that make it. And you'll make it in solution, and then it reacts. So the thing about our carbene is it is neutral, and it is both a nucleophile and electrophile. So it's really weird, because it's going to have an empty orbital, but it also has a lone pair. So it's going to be able to attack and be attacked. So that's going to be our carbene. And we have these different reagents to make them. So these are 3 different sets of conditions. We can have our diazomethane, which is CH2N2, is this thing. That weird looking thing. And when in the presence of heat, that's not heat, light, H nu, heat, our triangle, or usually copper metal, some other metals have been used, but some sort of metal catalyst, we can actually break our molecule in half. We can lose nitrogen gas. So to try to imagine how that would happen, I need to think of a resonance structure. So I'm going to say, all right, if I draw this resonance structure, I start at the lone pair. Nitrogen cannot have more than 4 bonds. So when I make this triple bond, I need another bond going away, putting the negative charge on carbon, right? Because nitrogen is in period 2, row 2. It cannot exceed its octet. It doesn't have d orbitals. It can't do it. Nitrogen cannot make more than 4 bonds. It's not possible. So I end up with this resonance structure. Why is that not my major resonance contributor? Like, why was this the structure that I drew? Why is that my major resonance contributor? Yeah, what about the negative charge? It's on the more electronegative atom, right? So that's the major resonance contributor, meaning this is going to be more stable. This is closer to the reality of what our molecule actually looks like, but the negative charge is also on the carbon. This is going to be the more reactive looking version. This is the one that we need to draw in order to explain our reactivity. So in the presence of usually heat, although that's very dangerous, in heat, light, or with a metal catalyst, we're going to just lose nitrogen gas. So both electrons go to that nitrogen. So we're taking this negative charge away from it. We're taking those electrons away from that carbon, but that carbon keeps that lone pair. And then this is the reagent that will then do our syn addition. So that's how we're making it with the diazomethane. So something to note about diazomethane is that it is highly explosive. It is very, very dangerous. And it, up until, when did the Nagib paper come out? Is that last year, 2 years ago? When did they publish that iron carbene paper? It was 22, okay, so 2 years ago, they illustrated that we no longer need our really dangerous reagents. So, woo, OSU. They did, this is really, like, until 2 years ago, people were still playing with explosives if they were trying to make a little triangle. If you wanted cyclopropane, you were doing dangerous things. So 2 years ago, OSU published that they found this way, a better way, to make the carbines, which, hindsight, I should have actually added it in here to have like the little plug. But, so they have this other way of making our carbines that is gonna be safer, because these are very explosive. And then, fun fact, after they published it, then the Nobel Prize winner, David McMillan, then started publishing carbine research afterwards. So like, we influenced a Nobel Prize winner. How cool is that? So, or at least that's the narrative that I'm gonna tell, because that's what I believe. So, that's the deal with our diazomethane, it was really good at making these, like for tens of years. I actually don't know how long when this reaction was invented, but for a very long time, this was considered like state of the art. Like you just were playing with explosive things, most likely, if you were trying to make your cyclopropane. It was so good at doing this. You just had to have a blast shield up to make sure that you didn't lose limbs. That was the diazomethane. There were some other reactions. So this is known as the Simmons-Smith reaction. And so this is also a good reaction that was they were trying to address the issue of the diazomethane explosive problem. But it is using like zinc and copper metal, and like having this is a little more expensive, and it just, depending on if you're in California or not, that's a joke, is going to say, I should finish the joke, is whether or not this is carcinogenic. So California has, I'm so sorry, I'm really weird today. California has really strict regulations on what determines something to be determined levels of safe. So if you look on different reagent bottles, it'll say, in California, this is believed to potentially be a carcinogen. And it's just really funny because it's like, only in California. Everywhere else, you're fine, is the joke among chemists. So I'm so sorry. We're going to move on. I don't know what is wrong with me today. Yeah, so if you add this reagent, just know it also makes carbines. So it makes that. You don't need to know the mechanism for that one. This one is reasonable. You could know this one. This is, however, going to make a carbenoid. So our carbenoid means that it's like a carbene. So the carbene is truly the CH2 with a lone pair. Carbenoid is saying anything that looks like that. So carbon with anything attached to it with the lone pair. So if you want to have halogens on it, so see here, these are hydrogens that were added on. You can have halogens instead. That means you need to go through the carbenoid so that we are making that Cl2 with the lone pair. That is your carbenoid. So the way that that is happening, the reason that I said that that is something that you could reasonably know, you would want a bulky base, a non-nucleophilic base, usually terbutoxide, and that is going to remove your proton. So you're going to be able to do acid-base chemistry with that chloroform. For the sake of space, I'm going to abbreviate this. So that you get this carbon anion, similar to here, where you had carbon with a negative charge and a leaving group. Here I have carbon with a negative charge and a leaving group. So then it's just leaving group leaves. So these are how we synthesize our carbene precursors. So the benefit here is it makes our triangle. It makes our cyclopropane. This is the only way that we know how to make a cyclopropane. So and we being this class. So if you see a triangle at any point, you see that cyclopropane, carbenes. That is our way of making that functional group. It's the only way we know to make that, well, it's not a functional group, that motif is to make that carbon ring. Epoxidation, the process of making an epoxide, is done with MCPBA. There we go. So that's going to be our reagent. And again, it's going to do a syn addition to make the epoxide. So the reagent that is doing the reaction is going to be that MCPBA. That's what's going to add the oxygen. The sodium hydroxide is just going to make it faster. So sodium hydroxide just makes it faster. It's not needed. Okay. So let's actually talk about our syn mechanism then, like what's actually happening. Good news is it's all concerted, so it's just one step. So it's actually pretty easy. It's going to be our alkene attacks the electrophilic atom. And then our electrons come back down. Actually, wait, that's got to be the nucleophilic atom because it ended up on the other side. We attack our electrophilic atom. And then our nucleophilic atom attacks the more substituted side of our double bond. So instead of it being we attack the atom and then the electrons go away or have a lone pair double back, instead it's the bond is now what is coming in and attacking that carbon. So it's like essentially these are just sitting down on top, like X and Y are just sitting down on top of the double bond, right, to make that bond. And it happens on both the top and the bottom. Because remember, we are sp2, we are planar, so there's nothing to stop us from adding to both sides. So we will add to both sides. Okay. So for all of these, that is the general mechanism. Like those are the arrows that you're drawing. So let's talk about some specific steps that are going to have that different mechanism to consider. No, we won't. We'll do that next class. Next class, we'll talk about our specific mechanism steps. Have a wonderful day.